Okay, in 16.6, we're going to look at weak acids. These are ones that partially ionize. They're going to have a very small K. All right, they have what we call a Ka. A is for the acid there. That's our acid dissociation constant, and it is the exact same thing as the K's from the previous chapter, except for these are going to go for a very particular acid and how the acid dissociates. If you have a smaller K, it's a weaker acid because it means that there is less of a shift to the right. Okay, so if you look at this chart here, notice how in all, I know they're kind of blurry, but all of these reactions are written where you have the acid, you can write the water if you want to, and they fall apart into the H plus and then the F minus, or the H3O plus, and then whatever the conjugate base is. So all of these here, if you look on yours, it'll be a little bit clearer. They fall apart into an H plus and whatever the conjugate base is there, or the other end of the H plus, okay? The larger the K value, like I said up here, the stronger the acid. All right, so now we're going to figure out our practice problem here. Okay, a student preparing a 0.1 molar solution of formic acid, and I give you their formic acid, measure the pH. The pH was found to be 2.38. I want to know what is the Ka. So here we're working a little bit backwards. Normally you're going to be given the Ka, and you're going to have your products over your reactants, and you'd solve for, say, the H plus concentration, or you'd solve for the equilibrium concentrations of something. Okay, well here I know that I start with 0.1 molar. All right. And I'm not going to have any of this. I'm not going to have any of that to start. These are all going to be very easy because we're all going to be shifting to the right pretty much. All right, because you're not going to have any of the products when you start for any of these. Now, they do tell me that my pH is 2.38. So if my pH is 2.38, that means I know my H plus concentration. If I know my H plus concentration, that means I can know what that is going to be at equilibrium. Okay? Actually, I should probably go the other way. That is going to be at equilibrium. All right, so I know my shift here is going to be minus x plus x plus x. Okay, really all I want is the Ka. All right, so I need to first figure out what my H plus concentration would be. Well, that's what we're doing, 10 to the negative 2.38, which will tell me that that's going to be 0.00417. Well, if that's 0.00417, this one's 0.00417. Which means my shift here is going to be minus 0.00417, which means I'm going to be left over with 0.00958. All right. And all I do is I plug them in. So I got Ka is products over reactants. It's my H plus and the COOH and the HCOOH on the bottom. And I plug in my numbers. So I'm going to have 0.00417 times 0.00417 all over 0.00958. And we should get it to be 1.82 times 10 to the negative fourth. And they should be small. If you have a Ka for the acids, they should be small numbers, okay? Because they are weak acids. As this one is a weak one. Okay, how do I know it's weak? It's not one of the strong ones. Okay, so all weak acids have very small Kas. Okay, so I want you to go ahead and try the next one. Okay, you're going to calculate the pH of a solution of 0.2 molar of the HCN. The Ka value for that is in Appendix D. All of these Ka values are known. They'll either give them to you in the problem, or they'll be in the appendix if you're doing the homework problems. Okay, so I know it's HCN. I know that's a weak acid. There's my Ka. Figure out the pH. Well, if all you want is the pH, then all I got to do is get my H plus concentration. I could care less what the rest of the stuff is. And that's kind of most, or how a lot of this chapter will go. All right, so go ahead and try the next problem. Okay, so doing all of that, all right, you got your HCN, pulling apart into H plus and Cn minus. I do my ice table. Okay, remember you can get rid of that minus X because it's a small Ka. I should get a pH of 5. Okay, now looking at percent ionization. Percent ionization is another measure of an acid strength. Okay, the stronger the acid, the greater it ionizes, meaning the more ions I make. So the higher the percent ionization, the stronger the acid. All that is the amount that's ionized over the original times 100. So we have the amount of our H plus equilibrium over the original times 100. You can also, on a kind of side note, use your Ka to calculate your pH. Here again, you're only looking for the H plus value when you're doing equilibrium. This should actually kind of be up in the practice problem, because that's kind of what we did. That's kind of in a bad spot. I probably should fix that. Oh well. All right, on to percent ionization and why that works the way it works. Okay. Percent ionization decreases as your concentration increases. So we see our reaction here of HA falling apart into H plus and A minus. You'll do this a lot. Okay, that's an acid. Acid breaks apart into the H plus and A minus. As I increase my concentration, what happens to my percent that's ionized? Well, my percent that's ionized starts to decrease. All right, so for a weak acid, okay, as my amount or concentration of the weak acid goes up, the amount of H plus in equilibrium goes up, all right, which means my percent that is ionized goes down. All right, if you double the HA or the amount of the acid originally, it does not double the amount of H plus that you have. Okay, it doesn't work that way. So how this kind of works is that you end up having more particles on the right side of your reaction. And as the diluted reaction shifts to the right to make more particles, okay, it shifts towards the side with more ions. So you end up shifting more and making more of these H plus, which means my percent ionization is going to go way down. Okay? So I'll show you an example here. It's kind of confusing until you see the example and go, oh yeah, look at that. Okay? Okay, we're going to do the percent ionization for the HF molecules ionized in a 0.1 molar HF solution. And then we're going to do this in a 0.01. All right? So if I have a 0.1 molar solution, none here, none there, plus X, minus X. Okay? I'm going to have my K equals X squared over 0.1 minus X. Well, I really don't care about that, so really it's just 0.1. The Ka for this is going to be 6.8 times 10 to the negative fourth. Multiply that by 0.1, take the square root. My X is equal to 8.2 times 10 to the negative third. With the percent ionized, it's going to be my H plus over the HA times 100. And I'm going to have 8.2 times 10 to the negative third is my H plus, because that's what X is. And my HA is 0.1 times 100. It's 8.2%. All right, 8.2% ionized. Now we take and we're going to decrease the concentration. All right, I decrease the concentration. Basically, all you're doing is you're changing this from 0.1 to 0.01. Still the same Ka. Now I get 2.6 times 10 to the negative third. Put 2.6 times 10 to the negative third over 0.01, and I have 26%. So what happened there is our concentration went down, but our percent ionization goes up. The more and more you dilute it, the more and more it actually ionizes to kind of shift and undo the fact that you're diluting it so much. I'm diluting it so much, think of it like I have so much more space. It shifts to the right to make more of those ions, to take up more of that space, to interact more with the water, if that helps. Okay, the last thing we're going to look at is polyprotic acids. Polyprotic acids are things that have more than one hydrogen, and they're written to be more than one ionizable hydrogen. You can have Ka1, Ka2, Ka3. It doesn't really matter how many. Okay, it is based on what the acid itself is, whether I have H2SO3 or whether I have H3PO4. Okay, so that's what the different Kas are for. All right. It is always easiest, though, to remove the first hydrogen, okay? And Ka2 is always smaller than Ka1, all right? They will often differ by at least 10 to the third, all right? If we look at this chart up here, we go from negative fourth to negative fifth to negative seventh, all right? We tend to kind of get, especially more and more as we have more and more Kas, it is harder and harder to remove them, all right? You go from H3PO4 to H2PO4 minus to HPO42 minus. You're losing more and more of the hydrogen, or one more hydrogen each time, okay? Okay, for example now, and then we're done. The solubility of carbon dioxide in pure water is 0.0037 molar. And it gives you a little thing about that. I'm going to produce, I'm going to take CO2 and H2O and make CO3. I don't really care about that. I want to know what is the pH of 0.0037 molar of the carbonic acid. So if I have 0.0037 molar, none of that, plus x minus x. Okay, I look up the Ka for the H2CO3, and it tells me the Ka for H2CO3, the first one, is 4.3 times 10 to the negative 7th. So I'm going to have 4.3 times 10 to the negative 7th equals x squared over 0.0037. Again, it's minus x, but we don't do the minus. Okay? And then x is going to be 4.0 times 10 to the negative 5th. And then end up with, that is my H plus value, because that's the x. So my pH is a negative log of 4.0 times 10 to the negative 5th. That'd be 4.40 is the pH. And I say I just want to do this whole thing about, you know, polyprotic acids and how they have more of the more H pluses to lose. Well, what you look at is if I were to take into account, okay, so if I do look at my second time here, I would be going into H plus and CO3 2 minus. This would be 4 times 10 to the negative 5th. That's how much of the HCO3 negative I have, minus however much I would turn into more H plus. Well, I would originally had 4 times 10 to the negative 5th of that, plus a little more, and none of that, plus a little more. The Ka2 for this is 5.6 times 10 to the negative 11th. I'm going to have 4 times 10 to the negative 5th plus x times x over 4 times 10 to the negative 5th minus x. You can do some algebra here. What you end up with is that your x is going to be 5.6 times 10 to the negative 11th. Okay, which is a very, very small number compared to 10 to the negative 5th. So you're not adding anything, which is why you're not adding anything to that H plus. All of the H plus in a polyprotic acid comes from the initial Ka. Very, 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 very few comes from subsequent Kas when you lose more and more H's. It's a little bit, but it's not very much. 10 to the negative 5th compared to 10 to the negative 11th.